This lecture deals with sampling and sampling distributions. Key topics include the difference between a sample and a population, taking a sample, sampling distributions, and the central limit theorem. So what exactly is a sample, and why do we use it? Well, we're rarely able to study everyone or everything of interest in a population. So we often have to rely on a representative subset of a larger population, that is, all cases of the group that we're trying to study. And that's called a sample. And sampling provides the basis for something called inferential statistics, that is, using the estimates based on a sample to make predictions about the values in the larger population. In order to talk about inferential statistics, we have to make a distinction between population parameters and sample statistics. So a population parameter refers to some characteristic of an entire population, whereas a sample statistic refers to the characteristics calculated on a particular sample. So for example, if we were interested in studying the income of the entire U.S. population, the average income of that population would be referred to as a population parameter. If we took a smaller sample of the U.S. population and studied their income, their average income would be referred to as a sample statistic. So note that we use different notation for parameters and statistics. Here's a table showing the different notation. Notice that sample statistics use Roman letters for their notation, while population notation uses Greek letters. Let's take a look at some common statistics that we look at and see how the notation differs for these statistics. So the sample mean in this case is y bar, and we can call the population mean mu sub y. That is, we use the Greek letter mu to refer to the mean. For proportions, we've been using p to denote the sample proportion. We can call the population proportion pi. Note that we're not talking about the number 3.14. We're talking about the symbol pi. It's just used as a symbol to refer to the statistic. We can also designate between a sample standard deviation and variance and population standard deviation and variance, respectively. So for the sample notation, we use the letter s, or s squared, to refer to the standard deviation and variance. When we're talking about a population variance or standard deviation, we often use the Greek letter sigma. So we rarely have sufficient resources to find the population parameters, but our goal in research is often to find them. And so we have to select a sample in such a way that we get reliable estimates of the underlying population parameters. And therefore the sample must be representative of the population. How do we ensure representativeness? Well, there's a number of different approaches to selecting samples, but only probability sampling allows researchers to use the principles of statistical inference to generalize from a sample to a population. And probability sampling is defined such that each element of the sample has a known probability of inclusion into the sample. And our purpose in collecting this sample is to select a sample that's as representative of the true population as possible. The most basic type of probability sampling design is something called a simple random sample, which has the following characteristics. It's chosen so that every member of the population has an equal chance of being chosen, and that every combination of samples has an equal chance of being chosen. In other words, samples are independent. Typically, when we collect a random sample, we use something called a sampling frame. A sampling frame is a list of all the members of a population, in which each member is assigned some kind of a number. And then some kind of a random number generator, perhaps a table, is used to select cases at random. So, for an example, let's take a look at this slide. It shows a hypothetical sampling frame with 20 cases. Let's suppose that we wanted to sample some number of cases from this population of 20 cases. We could use something like this. This is a random number table. Notice that it includes a list of numbers arranged into rows and columns. So if our goal was to sample from within that population of 20 cases, we can use this random number table. But we first have to decide on the number of digits to use for the table. Now, our population of 20 cases only needs 2 digits. So we don't have 100 cases. We can eliminate some of the digits from this table that we don't need. And so suppose that we decide to only focus on the first 2 digits. We can cross out the other digits and not use them. So let's just use the first 2 digits in this case. Next, we have to pick some kind of a random starting point. And so let's just say that I start it at number 88, roughly in the middle of the table. The next thing we have to do is we have to choose some kind of a direction to follow so that we can sample cases into our sample. And it really doesn't matter which way we go. We can go up, we can go down, we can go left, we can go right, we can go in a diagonal fashion. Any of these things is acceptable as long as we're consistent. So let's go up, and when we run out of space, we'll go to the next column to the right. So we can see that 53 is the next number going up from our random starting point. And we can see that that number isn't one of our 20 cases, so we can skip that one. We're not going to use this for our sample. The next one is case 63, and again, that's not in our population of 20 cases, so this indicates that we don't sample anything. Case 5 is the next number in order, and we can see that actually corresponds to one of our 20 cases, and so we're going to sample case 5 into our random sample. And if we use this pattern, we see that we can also sample cases 11, 6, 1, and then 2. And then we've got basically a sample of 5 cases. Okay, so how do we make inferences about a population parameter based on a sample? Well, we can use something called a sampling distribution. A sampling distribution is a theoretical distribution based on repeated samples. Now, in practice, we only take one sample. And so that's why it's important to know that a sampling distribution is only a theoretical distribution. It's based on all possible values, and so it allows us to determine the likelihood of the association between a particular sample and the behavior of samples in general. So to illustrate the sampling distribution, let's look at the sampling distribution of the mean. So suppose we took our population of 20 cases and we wanted to approximate its sampling distribution. Well, first of all, let's find the mean income for these 20 cases. That is the population mean. So suppose that this data set showed the incomes for all 20 cases. To find the average income, what we do is we're going to take all of the values for all 20 cases, add them together, and divide by n, which is 20 in this case. And that'll give us our population mean income. In this case, it comes out to 22,766. Once we've got that value, we can calculate the standard deviation. And you can see that that's calculated by taking each of the values of the income for each individual, for one of the 20 cases, subtracting the population mean, mu sub y, squaring the difference, dividing it by n, or 20, and then taking the square root. And so when we do the arithmetic there, we get a standard deviation of 14,687.5. Now, suppose that we took the sample mean of our 5 cases that we've sampled. And so here are the incomes for those 5 cases, cases 5, 11, 6, 1, and 2. So notice that if we add those values together and divide by 5, we get a value of 14,092.6. And you can see that our sample mean, 14,092, differs from the population mean, 22,766. The difference between the sample mean and the population mean is referred to as sampling error. And it's error that's basically due to random chance. That is, the random probability being selected into the sample through our randomization process. So there's nothing systematic about this difference. It's purely due to chance factors. So now, in constructing the sampling distribution, it's basically like asking, what would happen if we take repeated samples and we drew the same from the same population, and we drew the same size sample over and over and over again, and we graph the resulting distribution? What would it look like? Well, the result would be an approximation of a sampling distribution of the mean. That is, the distribution that results when all samples, based on repeated sampling runs of the same size, drawn from the same population, are plotted using the same graph. And so every statistic, the mean, the proportion, the variance, has a sampling distribution. But in our example, we're just illustrating the sampling distribution of the mean. So what I've done is I've approximated the sampling distributions by conducting something called a sampling experiment. I've done this 3 times. I've used varying samples. So I've used sample sizes of size 15, 17, and 19. And for each sample size, I've sampled them about 15,000 times. And I put them all into one data set and I graphed it. And so here's what the sampling distribution looks like based on samples of size 15 and 15,504 different samples. So notice that there's a normal distribution here, and it seems to be centered around the value of the true population mean, 22,766. Here's the distribution when we increase the sample size from 15 to 17. Notice that it too has a normal distribution, but it looks like it's slightly more tightly clustered around the value of the true population mean. Here's what it looks like for samples of size 19, and again taking 15,504 different samples. So we get the same basic result. Again, it's approximately normally distributed, centered around the value of the true population parameter. But again, it looks like it's a little bit more tightly clustered around the value of the true population parameter. So what kind of generalizations can we make here? Well, notice that all the sampling distributions follow a normal or approximately normal distribution, and they're all centered around the value of the population mean. That indicates that most samples are equal to the true population mean, but some sample means have very small values or very large values that are very far away from the middle. We can also calculate statistics based on the features of the sampling distribution. So, for example, we can get the mean of the sampling distribution, or we can get the standard deviation, and so on. So the mean of the sampling distribution is basically calculated by taking the sum of all the individual sample means across all permutations and then dividing it by the number of samples. So in this case, I'm using mu sub y bar to represent the mean of the sampling distribution. And it's calculated by taking the sum of all the values of the sample means, that is the sum of y bar, divided by m, which is the number of samples. And notice that that's equal to the true population mean, mu sub y. The standard deviation of the sampling distribution is known as the standard error, and it turns out that this depends on the sample size, because as the sample size increases, more of the area of the sampling distribution is clustered around the true population mean. In other words, there's less variation with a larger sample size, which makes sense because each sample has more information that's used for calculating the value of the sample mean, and each of these should better reflect the value of the true population mean. And so here are the formulas for the variance and standard deviation of the sampling distribution. The variance, which we'll call sigma squared sub y bar, is equal to the true population variance, sigma squared sub y, divided by n. And then if we take the square root of that value, we get the standard error of the sampling distribution, sigma sub y bar, which is just equal to the true population standard deviation, sigma sub y, divided by the square root of n. And so here's a table showing some of the characteristics of the sampling distribution for those three sampling experiments that we ran. And so notice that this column shows the means of the sampling distributions. And so looking at the sample means, we can see that they're very close to the true population mean. So you can see that for example, the mean of the samples based on samples of size 15 is 22,754.44. Recall that the true population mean is 22,766. So notice that they're very close in value. In fact, if we had the true sampling distribution, which is based on all samples of size 15 or 17 or 19 respectively, those values should be identical to the true population mean. Further, what this indicates is that although the individual sample means aren't equal to the true population mean, again because of sampling error, on average they're the same, and that's a statistical property called unbiasedness. Now let's take a look at the standard deviation. Notice that the standard deviation decreases as the sample size increases. And that's because, again, since we have more information per sample, we should get a better estimate of the true population mean, and so we should have less clustering around the value of the sample mean if we have a smaller sample size versus if we have a larger sample size. Now, if we take the true population standard deviation, which you'll recall was 14,687.5, and we divide that by the square root of the sample size, that is the square root of 15, square root of 17, square root of 19, we get the standard error. And notice that the standard error is very similar to the statistic we saw just a second ago, the standard deviation, right? So that tells us basically that we can estimate the average variation around the mean by using the true population standard deviation and dividing it by the square root of n. So notice that the standard error and the standard deviations are very close to each other. Let's talk about something called the central limit theorem now. We can summarize the properties of a sampling distribution using the central limit theorem, which tells us that as the sample size for each individual sample n gets large, the mean of the sampling distribution is equal to the true population mean. And it also tells us that as n increases, the standard error decreases in size. So this is something that we already saw from our sampling experiments. But the central limit theorem tells us how the sampling distribution behaves across all possible samples of the same size. So what's the significance of a sampling distribution? Well, it can be used to determine the probability that the sample statistic is within some distance of the true population parameter. And we can use that as the basis for statistical inference. So as an example, consider the following scenario. Suppose we knew the average income of an entire city. Suppose that we knew that the average income in the population was equal to $29,634 with a population standard deviation of 40,014. So imagine that we took a sample of 100 cases. Let's say that we wanted to know the probability that the sample mean income based on that sample of 100 cases is between 15,000 and 35,000. How would we do it? Well, first of all, we should start with a diagram. And so this diagram basically shows the distribution of our sample means, centered around the value of the true population mean, 29,634. So what we have to do is we have to take 15 and 35 and turn them into z-scores, and we have to figure out what area under the standard normal distribution corresponds to those z-scores. And so we're going to start by calculating the respective z-scores for 15,000 and 35,000. We're going to find their areas, and we're going to add them together. So notice that the z-score formula is going to change for the sampling distribution. It's not the same formula that we use for a normally distributed variable, although it has the same basic structure. Recall that in our earlier formula, we took some value, we subtracted the sample mean, and we divided it by its sample standard deviation. Well, this time we have a distribution of sample means, and we're going to subtract those from the true population mean and divide by the true population standard error. And so here's the formula that we use when we're dealing with a sampling distribution. In the formula, y bar is the sample mean. This is the thing that's actually being distributed now. So whereas last time we had a sampling distribution of some variable y, now we have a distribution of sample means. And so we're going to subtract from the value of the sample mean the value of mu, the population mean. So that's because the population mean is equal to the mean of the sampling distribution. We're also going to divide that value by the true population standard deviation, sigma. And that's being divided by the square root of n, the sample size. So the denominator of this formula is the standard error. And remember that we have to do this because the amount of variation in the sampling distribution differs based on the sample size. And so let's start with 15,000. How do we turn that into a z-score? Well, we'll take our raw score, our sample mean of 15,000, subtract the true population mean, 29,634, and we divide that by the standard error, which is equal to the true population standard deviation, 40,014, divided by the square root of n, or 100. And when we do the arithmetic, we get a value of negative 3.66. And so that tells us that 15,000 is over 3 standard deviations below the true population mean. And so we have to find the area under the curve corresponding to that value. And so 3.66 isn't listed, although we know it's between 3.60 and 3.70. And so as an approximation, let's just use a value of 0.4998. What about the z-score for 35,000? Well, if we take 35,000 and subtract the mean, 29,634, and divide that by the standard error, or 40,014 divided by the square root of 100, we get 1.34. And so that tells us that 35 is 1.34 standard errors above the mean. And we have to find the area under the normal curve corresponding to this. Now remember that we want column B, the area between the mean and the z-score. If you're confused about that, take another look at the diagram, which shows that we're looking for an area between the mean and the z-score. And so we look up our calculated z-score, 1.34, and we find that the area between the mean and the z-score is 0.4099. And so that's the one we want for this area. And so we would just add those two areas together. 0.4998 plus 0.4099 gives us a total of 0.9097. And so with a little bit of rounding, we can say that there's about a 91% chance that the sample mean is between 15,000 and 35,000.